Welcome. There are two very special buildings in the US, the Mormon Tabernacle in Salt Lake City and the Whispering Gallery in the US Capitol building. They're both oval-shaped rooms, and here's the amazing property they possess. There are two special locations in these rooms. I'll call it spot A and spot B. They have the property that someone stands at point A, let's call him Albert, and whispers something. All the sound waves from his whisperings, be very quiet whisperings, will go in all directions, but each sound wave goes off hits a wall, bounces off, and amazingly heads directly towards the second point. No matter which direction a sound wave's coming from, they all bounce off the walls and head directly towards B. So all the sound waves from Albert's whispers come and hit Bilbert's ears perfectly. But not only that, the distance each sound wave travels, so all these crooked paths, turn out to be exactly the same length. So each sound wave travels the same amount of time to arrive at B, so they arrive synchronously at B. So B can hear them perfectly well. So whatever A whispers, they all come and hit B's ears perfectly, and he can hear the whisper with absolute precise precision. This is what I mean by the reflection property of an ellipse. The special oval-shaped curve is called an ellipse, and they have this amazing property that all sound waves, no matter which direction they go, will bounce off the walls and head towards a second focal point, point B, and do so in exactly the same amount of time. Distances traveled is always the same. So I'd like to prove that today. All right, to begin with, I'm going to set the scene. I'm going to make sure I understand what I mean by reflection. I'm going to make sure I understand what I mean by ellipse, and then I'm going to go ahead and prove that ellipses have this property. All right, so first of all, let's talk about what is a reflection. And we'll go down a notch in sophistication, and just imagine I had a wall, straight wall. And obviously, if I throw a ball straight at the wall, assuming it's a perfect world, it doesn't lose energy due to inelastic collision and so forth, it will just bounce straight back at me if I come down at 90 degrees to the wall. So if it goes down with some velocity v, it'll head back to me the same velocity v, just opposite direction. Now if I give that ball a slight lateral motion, so I throw it at an angle, its vertical component velocity is still the same, and it's moving at a constant horizontal component. So my ball will come down, now vertically, it's going to travel at some velocity v, and in that time, we'll move some distance horizontally. But here, the vertical motion is going to be the same. It's going to follow the same property as if I just threw it directly, that its vertical component is still going to go directly backwards. But at the same time, it still has the same horizontal motion. So it'll still travel the same horizontal distance this way, but come back the same distance. Because that vertical motion is going to be the same magnitude, but in opposite direction. So that means my bouncing ball comes in at some angle, here's some angle, bounces off the wall, and since we've got congruent triangles here, I'm going to see it bounces off at the same angle again. So there's a property of reflection. What I mean by reflection is that any ball or sound wave or any object will always hit a straight wall with equal incoming angle and equal outgoing angle. Physicists will actually use a slightly different version of these angles, called the angle of incidence and angle of reflection. But basically, two equal angles. All right, that's a straight wall. Make sure I understand what happens when a ball bounces off a curved wall. And it's a little bit trickier. So let's do that. So let me draw a curved wall. Here's my pen. And imagine a ball comes in to bounce off this curved wall. What's it going to do? Obviously it's going to bounce back, but I want to understand what it means now. All right, bouncing is a very local phenomenon. That is all the actions happening right down here. So that means if I was to zoom that picture out, I've got some sort of picture like this. Whoops, let's make it be a little more flatter, I guess. And I have this ball bouncing in like yonder. Well, actually, that's a very local phenomenon too. If I zoom in right there, you can see that my wall is basically going to be, in my best human estimation, is going to be straighter and straighter and straighter. In fact, if I keep doing this and zooming in, the physical analysis, I might as well be assuming the ball is straight. So I've really gone to an idea of calculus, taking things to the extreme limit. And what's going to happen? The ball is going to come in, and as far as the ball can tell, right at its sort of zoomed in degree, that it's really bouncing off a section of a straight wall. You can't tell the difference between a curved and a straight in the ideal sense. Well, for a straight wall, we know it comes in with equal angles of incidence and reflection. So let's see what that means in terms of going backwards on this picture. That's the very zoomed in picture where, to all practical purposes for the humanist, if I zoom into some millionth power, it looks like it's bouncing off a straight wall. In a mathematical sense, if I zoomed into the infinite degree, whatever that means, now we're talking calculus, it looks like it's bouncing off a straight wall. Well, where's that straight line really? I guess I need a pen, a different color. There's the straight line. I guess the straight line is here, slightly curved. Here's the straight line, slightly off the curve. Over here, here's the straight line, slightly off the curve. What's really doing is as though the ball is bouncing off the tangent line to the curve at that point of contact. So, for a ball to reflect off a curved wall means, let's get my pen back. Here's a curved wall. The ball comes in, hits at some point, and then bounce off that point as though it's bouncing off the tangent line to the curve with equal angles of incidence and reflection. So be it a ball or a sound wave, to bounce off a curved wall is to come in at equal angles from the tangent line. Great. That's what reflection is. Now, what's an ellipse? Well, as per usual, I'm going to start off back a step. Ellipse is a special case of a circle, and how do I make a circle? So imagine I had a nail in the wall, and I took a loop of string, and I stuck one end of the string to the nail, brought it up, and stuck the other end back down to the nail. And if I took a pen, or pencil, and put it right at the end of the loop, and pulled the loop taut and swung it round, I'm going to start tracing a curve, And clearly, since I've got a sort of a fixed radius here, that curve's going to be a perfect circle. Well, an ellipse is exactly the same idea, except I just be a little bit funky with the ends of my string. So having both ends meet at the same point in the wall, what if I have one special point, point A, for one end of my string, and tie the other end of my string at point B? I will use a pencil to take that loop of string and make it taut. That is, I have a pencil at some point up here, and then I'm going to swing that pencil around, keeping the string taut, and that's going to trace a curve. Now, it might be fun to actually play with it, but what you'll find happens if you swing this all the way around, you'll get a squished circle shape. And there we are. That squished circle shape is called an ellipse. So what an ellipse is a curve with two special points, they're usually called the foci, focus A, focus B, such that each is the location of a pulled piece of string. Which means, here's the true definition, an ellipse is a curve with the property that for two special points A and B, any point P on that curve is the property that the distance between A and P plus the distance between P and B, so the distance between A and P plus P and B is a fixed constant. In this case, it's our length of string. So that's an ellipse. All right, now, what do I mean by the reflection property of an ellipse? Well, clearly you can start to see the connection now. Whoops. Cancel, press the wrong thing. So I have an ellipse. Here's my two foci, A and B, Albert and Bilbert. I claim that the Mormon Tabernacle is actually made as though it's from a pulled piece of string or a rope or something. All right, so the claim is that for the reflection property, any sound wave coming from Albert's position will travel in a straight line, will bounce off the wall. What we learned by bouncing is that imagine I had a tangent line to the ellipse right at that point with equal angle and equal reflection. So it comes off at equal angle. And the amazing thing is apparently that equal angle reflection heads the sound wave directly back at B. So no matter where I go, I've got to prove that the angles at the tangent line to that point on the ellipse are always equal. That's a very bad picture. That will force the sound waves to actually bounce back at B. Now, since these lengths are the same length of string, I've actually got my additional property that all the sound waves travel the same distance to arrive at B. So what I need to prove, the reflection property of the ellipse, that at any point on the ellipse, the line connecting that point to each of the foci makes equal angles of incidence and reflection. Whew. Now I've just described what I'm going to prove. Let me start the video of actually proving this. All right. I actually love this proof because I'm coming at this in a completely strange, unexpected way. I'm going to go to the beginnings in some sense and talk about straight walls. All right. So imagine, here's my problem for the moment. There's a wall, and I have a dog who's currently at position A and would like to walk to position B. And being a dog, the dog would first like to walk to the wall and then walk over to position B. So the dog is going to walk some straight line to some point on the wall and then head over straight to B. My question is, which point of contact should the dog head to so as to give the shortest distance from A to B via the wall? So you might wonder, okay, maybe the dog should go directly below the point B and then head straight up. Or maybe the dog should go directly below the point A and head on over. Maybe the dog should go to the midpoint twixt A and B or something and then head over. Who knows? But what position along the wall gives the shortest path from A to B via the wall? Okay, I'm going to answer that question two different ways, two strangely completely different ways, and we'll see that the reflection property of the ellipse pops out from our analysis. So let me just redraw my picture. Solution number one, A, B. Maybe I should keep a copy of this picture because it seems to be a semi-decent one, unlike me. What I usually do. All right, here goes. I don't know where the special, I'll keep doing that. Don't know where that special point is, but I'll do this in blue. So one thing to note, it's very hard to deal with crooked paths. So what I'm going to do is inspired. It probably takes a long while for someone to think to do this trick. And once you see this trick, then you'll think to do it in other situations. But some bright spark at some point realized, well, instead of talking about paths that go from A to B, what if we looked at the reflection of part B on the other side of the wall? Here's the point B primed. That means if I walk to some place point on the B on the wall here, the path to B can be mirrored by a path to B primed. And it's nice and perfectly symmetrical. This length equals this length. So walking from A to B via the wall is the same as walking from A to B primed via the wall. This length plus double dash is the same as this length plus the other double dash. And conversely, if I give a path that goes from A to the wall and then that point on the wall to B primed, that really does correspond to a path that goes from A to the wall and then that point to B. And all the lengths match that matches itself, and this length matches this length. So actually, the shortest path from A to B is really given by the shortest path from A to B primed. And I know the answer to that problem. What's the shortest path between 2 points? Well, it's the straight line path. So that means to find the special place on the wall the dog should walk to is you should imagine the wall as a mirror and walk to the reflection of B primed in that mirror. That gives me this point here. But of course the dog's not going to be able to walk through the wall, it's not going to be able to walk through the second position, instead it will turn up this way. Alright, but let's notice something here. Look at this angle here in messy green, my picture's bad. Well, I've got vertical angles from a pair of crossing lines, that equals this angle here. So, but since B prime is just a reflection of B, this angle underneath the wall is the same as this angle above the wall. So actually, the answer to the problem is the dog should walk to the special place B that gives equal angles of incidence and reflection, as though the dog were actually a bouncing ball off the wall. So the shortest path from A to B via the wall is at the point that gives equal angles, just like reflection. Alright, that's answer number 1 to the problem. Here's answer number 2. And did I indeed save my picture? Yes, clever me. Answer number 2 to the very same problem. What I'm going to do is I'm going to draw ellipses with A and B as foci. Now if I did a very short string that barely reaches across, I'm going to get a sort of a fairly flat oval. There's a short string. If I did a slightly longer string, I'd get a slightly bigger, I said oval didn't I? I should have said ellipse. I'd get a slightly bigger ellipse. That corresponds to a longer piece of string. If I did a really long piece of string, I'm going to get a huge, big ellipse. There's a longer piece of string. All right. Now I want to find the point on the wall that gives me the largest distance from A to B. All right. Here goes. That's the shortest distance from A to B. Silly me. Well, clearly, this bright blue ellipse corresponds to some crooked path, as though I'm walking to the wall, but it's not big enough to hit the wall. This green ellipse does correspond to some crooked path from A to B, but there's a whole bunch of different crooked paths I can choose from. But again, they're not quite long enough to hit the wall. No matter what I do, they don't hit the wall. Let me choose the size of ellipse that just hits the wall at some special point. There. This is a length of string that corresponds to hitting the wall just perfectly. All right? Now the red ellipse doesn't do much for me. It gives me a point on the wall. Yes, no doubt, it's a point on the wall. But it's giving a path from A to B that's actually longer than the matching yellow path. Well, hang on, what am I doing? This is the point. Silly me. Sorry. Here's a red path. Gosh. There it is. That gives, if I did a bigger ellipse than the yellow one, I'm getting a point on the wall that corresponds to a longer piece of string and therefore is longer than the yellow one. So this yellow ellipse is the first ellipse that touches the wall, and it's the smallest ellipse that I can use that touches the wall. That is, this yellow path is indeed the answer to my dog walking problem. It's the smallest length that just touches the wall that gives me a crooked path from A to B via the wall. There it is. That tells me that the special point I'm looking for this dog walking problem is this point here. Well, now I've got two answers to the same problem. This point P for the ellipse version must be the same answer as this point B for this walking version. That is, I've got a situation that describes the reflection property of the ellipse perfectly. Here's a point on the ellipse. The wall is the tangent line to this ellipse. This is the one that just touches the ellipse. And we proved that it is the answer to the dog walking problem. That means if it's the answer to the dog walking problem, it has this property over on the left. The angle to the left is the angle to the right from this line that just touches the wall at the point of contact, the tangent line, the point of contact. This is exactly what we needed for the property of the ellipse. And just to make myself clear, because my diagrams, as per usual, are messy, if I take any old ellipse, here's any old ellipse, point A, point B, it's two foci, I choose any point P on it, there's a point P, its tangent line corresponds to a dog walking problem. Go from A to that blue line, back to B at some point that gives the shortest distance. So this black ellipse must be the first ellipse that touches this tangent line, which means it is the answer to the dog walking problem, which means it has the same property as the first way you analyze the dog walking problem, equal angles about either side of that tangent line. That is, this ellipse is having the reflection property I was hoping for. Any sound wave from A hits the tangent line, bounces off at equal angles, and hits directly towards B, and does so at the same distance, no matter where I'm to be doing my analysis. There it is. There is the dog walking problem, the reflection property of the ellipse via dog walking. Now, the wonderful thing is, there are actually reflection properties for other conic shapes, the parabola and the hyperbola, and they're just variations of the ellipse. You can actually prove them in the same sort of way. Can you find the right dog walking problem to solve the reflection property for hyperbola, or the correct dog walking problem for that for the parabola? Which means you probably need to understand what those reflection properties are, and I'm going to be shameless right now. If you go to my website, I actually wrote the third volume of my series, which covers the whole high school curriculum, actually has the final chapter on conics and how to understand ellipses, parabolas, and hyperbolas, and explains all the geometry of all the reflection properties. So you might want to look at chapter 3 if you get volume 3 if you get really, really stuck. All right, there we go. Thanks so much.